to get it all on the table. And that is, we took our linear system so far down into row echelon form, which have the ones on the diagonal, or at least the ones in the pivot positions, but which have sort of other stuff cluttering up the top triangle of the matrix. We could take this a step further and take our matrix down into what's called reduced row echelon form, which, by the way, is where the RREF command on your graphing calculators comes from, reduced row echelon form. And in a reduced row echelon form, not only are all the pivots identified and all of them are equal to 1, but they're also all alone in their column. In each pivot column. In other words, each pivot column has a single 1 in it, and all the other entries are 0. So what that means is, instead of stopping our row reduction when we have our pivots, as we've done here, we're going to keep going. And in addition to having cleared out everything underneath the pivots, we're also going to clear out everything above the pivots as well. Shouldn't take too many steps in this example, so let's just do it. Let's say I want to clear out the green one, the green pivot in the middle. What can I do to accomplish that? What row operation? Yeah, so what I'm trying to do is I'm trying to clear out this this thing that's above the green pivot.
Maybe add the second row, or subtract the second row.
Subtract the second row from the first row. Right. And that will clear out the one that's on the top there. So what will we have here? 1, 0, 0. 0, 1. And then I've got negative 2/3 here. And negative 2 minus negative 2/3 is negative 6/3. Plus 2/3, so negative 4/3. And then 1 minus 2, negative 1. Okay, so that's cleared out the green pivot so that it's all alone in its pivot column. Now to clear out the pivot down here in the lower right so that it's all alone in its column, I've got to, and luckily this is really easy because of the 0 at the end of its row right there, but I've got to add 2/3 of the third row, into the second row to clear out the negative 2/3. And then add 4/3 of the third row to the first row to clear out the negative 4/3. That's going to give me a 0 in both of these entries. 0, 0. But notice the entries on the far right, to the right of my dividing line, aren't going to change because I'm just adding multiples of 0 to them. So now that we've cleared out everything above the diagonal in addition to everything below the diagonal, now we have the famed reduced row echelon form of this matrix. And sure enough, the reduced row echelon form of this matrix, what did we call this particular matrix a minute ago? What kind of matrix is it if it's 1s on the diagonal and 0s everywhere else? Identity. By the way, this has something very specific to do with the nature of the solutions of this system. If we can row reduce a matrix down to the identity matrix, how many solutions did that system have? Well, how many solutions did this system have? 1. This system had a unique solution. There's only one value of x, y, and z that makes these 3 equations true simultaneously, right? There's a unique solution to this. And the reason there's a unique solution is that we can row reduce this matrix all the way down to the identity, because in equation form, what does the identity matrix do for us? It tells us that x is equal to this number, and that y is equal to this number, and that z is equal to this number. So the purpose of the identity matrix is to be a harbinger of a unique solution, if you like. So the identity matrix implies unique solution. It's a hint of things to come. But I did want to say before we took our break today that what happens when we don't have a unique solution? We're going to end up with not a unique solution in the cases where our matrix does not row reduce to the identity. There's the contrapositive again. Identity matrix implies unique solution. So not unique solution must mean we didn't get an identity matrix when we row reduced. So let's just look at a very quick example of that and see how we can use the idea of pivot columns to actually write a solution which is not unique, in a similar way to what Group B did in yesterday's work. So let me just get a blank page here. So here's a system, and let's make it a 3x3 system again. X plus y equals 10. Y plus z equals 5. And x minus z equals 5. So there's a system. And again, the question is solve. Simplest action word in all of mathematics, solve. So we turn it into a matrix. And the coefficients are something like 1, 1, 0, 10, 0, 1, 1, 5, 1, 0, minus 1, 5. Let's apply our strategy to the solution of this system. I tried to set it up so we didn't have that many steps this time. Where do I start? Let's start again the first column. Let's try to make this first entry in the first column, which has nothing to its left. Let's try to make it a pivot.
Subtract row 1 and row 3.
Subtract row 1 from row 3. Yeah. That will accomplish clearing out everything we need to clear out underneath that entry in order to make it a pivot. So, row 3 minus row 1 will accomplish that. So that now I'll have 1, 1, 0, 10, 0, 1, 1, 5, and then 1 minus 1 will be a 0, 0 minus 1, negative 1, negative 1 minus 0, negative 1, and 5 minus 10, negative 5. And now we have our first pivot, which is good. It means we're making progress. That also means that as of now, we get to totally forget about the first column. So we're going to lock that, the first row, lock that in place, and the first column, lock that in place. Now what?
Wouldn't it be 5 not negative?
I subtracted row 3 minus row 1.
Oh, I thought it
So
was
that's
4.
5 minus 10. Yeah. Yep. So what do I want to elevate into a pivot next? Where's my next pivot going to be?
Subtract row 2 and row 3. Add row 2.
Let's add, because again, we want to, I'm focusing on that one that's right there in the middle now. I'm going to try to make that a pivot because it's the upper leftmost thing that's left in my matrix now that I'm freezing the first row in the first column. And so I want to clear out what's underneath it. Oops. And to clear out what's underneath it, let's add the second row to the third row. Row 3 plus row 2. And my first row is frozen at 1, 1, 0, 10. My second row doesn't change, 0, 1, 1, 5. But when I add the second row to the third row, I get 0, 0, 0, 0. So something happens here that didn't happen before. By the time I've now discovered this second pivot, and we have indeed made this into our second pivot, now what? What do I have left to do?
You can only go backwards again.
We can only go backwards. We can't make any more pivots because there's nothing in that third row that's non-zero. Right? And in order to make a pivot in that third row, we need a non-zero entry to work with. So we can't do it. So we're done as far as discovering pivots. This matrix is in its row echelon form. And so really, only the first and the second column are pivot columns. So let's keep score over here. Pivot columns are the first and the second. That means, so keeping in mind what pivots are intended to tell us, that tells us that we can solve for the values of the variables that correspond to those columns. We call those bound variables. These are variables that we're going to get expressions for. And what are those two variables if the first and second columns are the pivots? X and Y. The variables that correspond to those two columns are bound, and so we can find expressions for X and Y. But that means that the third column, the variable that corresponds to the third column, is not a bound variable. Variables that are not bound are free to take whatever value they like. So we call them free variables. And so that third column corresponds to what we're going to call a free variable, Z, which means that when we write the solution of this system of linear equations, rather than being able to say Z is equal to something, we're just going to say Z is free. Z can do whatever it wants to do. But as soon as we choose a value for Z, that value will determine the value for X and the value for Y, because those are bound. Those we can't choose freely because they depend on the value of other things. But because we now have a non-pivot column, we have a free variable in our solution. To finish writing the solution now, let's go back to our system. And let's finish the process of putting it into not just row echelon form, but reduced row echelon form. That's only going to take one more operation. What do I need to do to put this system into reduced row echelon form? Where every pivot is alone in its column. Close. We're just one step away because we need to clear out not just the entries underneath the pivots, but the entries above the pivots. And there's one entry that's non-zero that's sitting above a pivot. It's that one in the first row, second column. So to use the second row to clear out the first row, we'll just subtract. Row 1 minus row 2. And this will get us into reduced row echelon format, which is the easiest way from which to write your solution set. So the second and third rows remain the same as they were, 0, 1, 1, 5, all zeros in the last row. But then the first row, subtracting row 2 from it, gives me 1, 0, negative 1, 5. Spot check me on that arithmetic. And again, the two pivots are still our two pivots, but now because they're alone in their columns, this is the reduced row echelon form. Let's translate that back to equation form. X minus Z is equal to 5, and Y plus Z is equal to 5. But then this third equation is 0 equals 0. What does that tell us again? This was group A from yesterday? No, sorry, this was group B from yesterday. Again, 0 equals 0 in our solution tells us what? Yeah, this was the sort of the catchphrase for possibly infinitely many solutions. But at the very least, it tells us, it doesn't tell us that this is an inconsistent system. If this were 0 equals 27, as your group saw yesterday, then we would definitely have an inconsistent system. But 0 equals 0 is okay, because that's a true statement. So then to finish writing our solution set, we just need to get X by itself and Y by itself, which we can do just by moving the Z's from these equations to the right. So we find out X is equal to 5 plus Z, and that Y is equal to 5 minus Z. And that's another way to write the solution set of this equation. We need all three of those things, right? We say that Z is a free variable, so we get to pick whatever value we want for it, and there are infinitely many choices. Right? Any real number that we choose for Z will be okay, because Z is free. But as soon as we pick that value will determine what X is, just add 5 to it, and that value will determine what Y is by subtracting it from 5. So a free variable is free because it gets to have whatever value we want it to have. But as soon as we give the free variables values, those values determine the values of the bound variables. And the free variables are coming from the columns that do not have pivots. The bound variables are coming from the columns that do.